In the study of vector fields, we seek to understand the invisible flow that governs every point in a given space. By analyzing how vectors change from one point to the next, we can describe complex physical phenomena like fluid currents, magnetic forces, or atmospheric expansion. To understand these fields, we look at two primary characteristics: how much the field is expanding and how much it is twisting. Divergence acts as a measure of source or sink behavior at any specific point. If a field has positive divergence, it is expanding outward, much like air being pumped into a room. If it has negative divergence, it is being compressed. A stable, or incompressible, flow has zero divergence, meaning the amount of stuff entering a region is exactly equal to the amount leaving it. Curl describes the rotational tendency of the field. It tells us if a tiny paddle wheel placed in the flow would start to spin and in which direction. A field with zero curl is considered irrotational, meaning it moves in straight lines or radial patterns without any twisting motion. Different mathematical definitions create distinct physical patterns, which can be categorized into a few primary archetypes. The position or source field represents a pure radial outward flow where every vector points directly away from the center. It is characterized by a constant positive divergence, indicating a source at the origin, but it has absolutely no rotational twist. The rotational or cross-product field represent pure circular motion around a central axis. In these scenarios, the field does not expand or compress at all, resulting in zero divergence. Instead, they possess a constant curl or spin. Depending on the specific configuration, this spin can be counterclockwise, positive curl, or clockwise, negative curl. Because vector fields are abstract mathematical constructs, we use specific visual tools to build an intuitive understanding of their behavior. Quiver plots are the most common way to see a field statically. A grid of arrows is drawn across the space, where each arrow's direction shows which way the current is moving and its length or color indicates the strength or speed of the field at that specific spot. To see the field in action, researchers use dynamic animations where virtual particles are dropped into the flow. These particles move frame by looking at the velocity of the field at their current location and stepping forward a tiny bit in that direction. Modern simulations often include boundary handling, where particles that drift too far away are teleported back to the center to maintain a continuous visual flow. This allows observers to watch the real-time current of a field, making it easy to distinguish between an expanding source and a swirling vortex.